The next topic that will be introduced is this concept of enthalpy. So we see here enthalpy is defined as the internal energy plus the product of pressure and volume. So enthalpy is related to the internal energy of our system, but we can summarize the enthalpy term over here, where we see that it's not only the value E here for the internal energy of our system, but also this term, which is a work term with gases. So we have this pressure of the gas changing in volume. So um, this type of work can be done. When we have a sealed container, we can measure this, but usually in an open container, the only work done will be by the gas pushing on the surroundings. So if the system is doing negative work, the system's doing work on the surroundings, or if the surroundings are pushing on the gas in our system, that would be a positive work being done on the system. So this is what happens in an open container. But if we have a vessel here that is fitted with a piston. So here's our piston, and this is atmospheric pressure, or the pressure before any reaction occurs. If we were to take some zinc metal and place it into this reaction vessel here, which has hydrochloric acid, which will dissolve the zinc in this fashion here. So this is the reaction that is occurring here. H2 gas is generated, and when this hydrogen gas is generated, it will move this piston. So we can actually measure the work that's done using this relationship here, where work is equal to negative P delta V. So the change in volume times the pressure value. And we can see that if the system does not change volume, it does no PV work. So that brings us to another relationship. So when the change in volume is zero, this work portion of the equation will disappear, and we can see that at constant pressure, right? So we have no change in volume, so we assume the pressure is constant. The change in enthalpy, the delta H, we can equate that to Q. So we can see here through this series of derivations that enthalpy, we know, is our change in internal energy times the work factor pressure time delta V, so P delta V. But since we have E equals Q plus W that we saw in a previous lecture, and now work equals negative P delta V, we can plug in these values so we can see this relationship here, where delta H is Q plus W minus W, but at constant pressure, that will simplify down to this here. So this is how this relationship is derived. And again, at constant pressure, the change in enthalpy, so the delta H, is always going to be equal to Q, the heat gained or lost. And just like we saw with our internal energy, our delta E, we can call a positive delta H an endothermic process, and we can call a negative delta H indicative of an exothermic process. So these terms are used as such. So let's take a look at sample exercise 2 here and see if we can use our knowledge of enthalpy so far to indicate the signs of these enthalpy changes. So our answers are either going to be positive delta H or negative delta H, and then we're going to indicate whether these would be endothermic or exothermic processes. So let's think about when an ice cube melts. So we have solid H2O, and that's going to turn into liquid H2O. So we go from a solid phase to a liquid phase, if we were to simplify this. And we definitely have to increase the temperature, right, to do so, because water is solid at 0°C, and then it's liquid above that up to 100°C. So we have solid to liquid, so we increase temperature. So this implies that we would have to add heat. So this would be a positive delta H, and we would call this an endothermic process. Let's look at part B here. And we're told that we have 1 gram of butane. This is the chemical formula for butane, is combusted in sufficient oxygen to give complete combustion. So we have a combustion reaction here. And if we recall, the general form of a combustion reaction will be our hydrocarbon, so butane plus oxygen, and that would yield CO2 and H2O. And any combustion reaction, think about butane and a lighter being lit, these will give off heat. So in general, we can just assume that a combustion reaction is going to have a negative change in enthalpy. So that would be a negative delta H, and it's going to be an exothermic process. Again, just from our knowledge that combustion reactions will give off heat. So we'll continue with the next topic in the next video.